Welcome to this session on the Simplex algorithm. Let's illustrate the algorithm with an example of a basic exercise, nothing too complex in the beginning. Here we have a company which produces two models of its product, the basic and the premium version. The basic version results in net revenues of 28 euros, whereas the premium version results in net revenues of 42 euros. Additionally, the company needs to cover for fixed costs of 2,000 euros. And the premium version is more labor intensive in its production and requires 20 minutes of work, whereas the basic version only requires 10 minutes. Furthermore, each version requires one frame, and the premium version an additional 120 grams of steel, and the basic version an additional 90 grams of steel. Then, what we know about the stock: the company has a stock of 200 labor hours available, as well as 50 frames and 51 kilograms of steel. Everything of these per week. How many basic and how many premium versions should they produce per week as to maximize their weekly profits? How high are these weekly profits? So let's work our way through this exercise step by step. So first we copy it. Now we take a look. The first step always is finding out which aspects can we actually influence. So what are our decision variables? Here we can see, if we take a look at decision variables, we have the information. We produce two models. So we'll have two decision variables. And if we take a look further downwards, question also is how many basic and how many premium versions should they produce. So this gives us the information that we have two decision variables, an x1, which is the amount of basic versions to produce, and an x2, which is the amount of premium versions to produce. So far for the first step, when we have the decision variables, we can formulate our objective and our constraint, each of them based on using those decision variables we just defined. This means later on there won't be any additional variables. We only will use the decision variables we defined in the first step. With this in mind, let's move on to the second part. It's the same text, but here we are interested in getting our objective function. So first, what is our objective? Here it clearly reads how many basic versions produced per week to maximize the weekly profits. And we have the profits for the first one of 28 euros and the profits or net revenues of 42 for the second one. Additionally, we have the information that they have fixed costs. So we need to write this information down, only by referring to our decision variables. So here we have, with this additional information, the objective maximize, that's the last part. Then 28 times x1, that's the net revenues per unit of x1, plus 42 times x2, that's the total net revenues of all x2, so all premium versions, minus 2,000, as we have the fixed costs of 2,000. We see this is our objective. We need to maximize this function. This function contains the variable part, which here depends on x1 and x2, and also on our net revenues. And we have the fixed version, that's our fixed costs. And we're only using those variables we defined in the step before. So we are only using our decision variables. This will always be the case. Okay, so much for our objective. Then in the next step, we're working our way through our constraints. We start with the first constraint. Here we can see the first part we find is on labor. It says 20 minutes of work for the premium version and 10 minutes of work for the basic versions. So that's the requirements. Then we have the additional information. We have a stock of 200 labor hours. So if I combine all of this, this means per unit premium I build, I need 20 minutes. So the overall time spent on premium versions will be 20 times x2. The overall time spent on basic versions will be 10 times x1. Both of them together, so the sum of both of those terms, needs to be smaller than our stock because, well, obviously we can only use so much as we have available. We cannot spend more labor hours because we do not have the workers for this. So the first constraint looks like this. 10x1 plus 20x2 is lesser than, and here we have the information 200 labor hours, but on the left side we're talking about minutes, so we need to convert the 200 labor hours into minutes, so it reads as 200 times 60. Well, we could leave it as it is. However, always makes sense, if possible, to work with smaller numbers. So we see here we can easily get this a bit simpler by dividing by 10. We get as a constraint x1 plus 2x2 is smaller than 1200. So this is our first constraint. Similar to the objective function, this, or in particular its left side, only depends on our previously defined decision variables. Okay, so far for the first constraint. For the second constraint, if we take a critical look, we see here the second constraint is on frames. And we have the general information. Each version requires one frame. So for each x1 I produce, I have one frame. For each x2, I have one frame. So the left side is x1 plus x2. That's all the frames I use. Then I have the information, I have a total stock of 500 frames. So that's a maximum of 500, or the right-hand side of our constraint will be 500. So that's what our constraint or frame constraint looks like. x1 plus x2 is smaller, lesser than 500. Here we cannot simplify this in any additional way. Okay, so then this also covers the second constraint. Let's turn to the third one. In the third constraint, well, we are only left with one additional part which we haven't yet covered, and that's the steel part. We know we need for the premium versions 120 grams of steel, and for the basic versions 90 grams of steel. And we have in the lower part the information that we have a stock of 51 kilograms of steel. Again, we see the problem. On the one hand, we work with grams. On the other hand, we have our stock in kilograms. So we need to make this comparable. But before we do this, let's just write down our constraint with the values from the text. So here it would read 90x1, because that's the requirement for our basic versions, plus 120x2, because that's the requirement for the premium version. This needs to be smaller. Then we have here 51,000, because, well, as I mentioned, 51 kilograms, the requirements are in grams, so we need to transform kilograms into grams, so we multiply with 1000. This then can also be simplified a bit. We can first divide by 30. Then we get the simplified version on the left as 3x1 plus 4x2 is lesser than 1700. That's a bit smaller and easier to handle. And well, if we then take a look at our text, we covered everything which given in the text. We have decision variables, 2, the amount of basic and premium versions to be produced. We formulated an objective function, and we formulated 3 constraints. So let's just summarize all these informations in a comprehensive model. If we do this, we get as our objective maximize 28x1 plus 42x2 minus 2000. So that, then there's the constraint, the labor constraint, x1 plus 2x2 lesser than 1200. We have the frames constraint, x1 plus x2 lesser than 500. And we have the steel constraint, 3x1 plus 4x2 lesser than 1700. We are more or less finished here, but well, we're not only covering for purely theoretical mathematical problem, we're covering for an economical, a real world problem. So we also have the underlying information as a, so to speak, lower bound, that both of our variables need to be 0 or larger than 0. Well, obviously we cannot produce a negative number, so this is just like common sense, and from a mathematical perspective this helps us to define a closed area, closed convex space, or closed convex feasible area. Okay, however, we're not going to work with this version. We will simplify this version, or basically just write this in a different fashion. The first way we can go is if we recall that everything which is linear, and our problem here is linear, meaning all the x's have an exponent of 1, so it's x1 to the power of 1 and x2 to the power of 1, always. Well, that's the basic idea. Simplex works only for linear problems, and linear problems can be noted in a matrix vector version. So we can write this problem also with matrices and vectors, and we get this objective function, which is basically the vector to the left are the coefficients from our objective function, and we have two decision variables, so that's the second vector with the x1 and 2. The same thing goes for our constraints. Here we have a matrix on the left containing all the coefficients from the left side, and we have a vector on the right containing all our stocks. Then, well, we have a last comment with x1 and x2 larger than 0. Again, this is a bit simpler as a notation, but we still go in a slightly different fashion when we work with our simplex. So we will again reformulate this a little bit to a slightly different looking tableau. Well, in the end, it's nothing so much different from our left side, the matrix vector notation. We have two important columns, that's the two in the middle, and here we have one column per decision variable. We only have two decision variables here, the x1 and the x2. That's why we have two columns in the middle. And in the first column of these, for the x1, we note all the values related to x1. With one exception, we are having a maximization problem here. So what we are going to do is we take our values from the objective function, so the 28 and the 42, and not copy them as they are, but multiply them with minus. So we get minus 28, and for the x2 we get minus 42. Again, that's the situation if we work with maximization problems. With minimization problems we would take them as they are. Then, below those numbers from the objective function, you see that's the row with the z in front. We could also call this row objective function. Below this we have the three constraints we have. Here we give an additional or generate additional new variables. In the end we don't need them really for our results. They have a purely, let's call this mathematical purpose. Yes, they can also be interpreted in a sensible fashion, but we won't go into this in this first introductory session. So here, just for each constraint we have here three constraints, we introduce a new variable. The new variable covers for each of the constraints. So again, summarizing this, we have in the second row everything related to our objective function, whereas the coefficients are noted in a negative fashion. Below this, we have the information for our constraints. So we basically copy the matrix from the constraints. Well, and finally, on the fourth column, the most right one column, we copy for the objective function any fixed costs, any fixed values, so everything which is not dependent on x1 and x2. And for all the constraints, we copy the right-hand side. Here in this case, needs to be noted, we can use this version when the problem actually consists of only lesser than constraints. However, this is no big deal because all greater than constraints, I can just multiply them with -1 and I get lesser than constraint. And even with equality constraints, I just have to think that, well, equality constraint is the same as being larger or equal to and lesser and equal to at the same time. So I can just reformulate all different types of constraints to read as lesser than constraints. I wouldn't do this if I have equality constraints, because there will be an easier fashion to cope with equality constraints. However, again, we won't go into detail on this topic here in this session. So for this part, just recall to use the simplex to build our tableau the way as seen here. For this, we would require only lesser than constraints. And then we copy the right-hand side in the right-hand side of our tableau. And the tableau, that's the part where we will work with in the next step. That's where we're actually going to use the simplex algorithm. So we copy our table, the tableau we had before. And our first task is to finding the so-called pivot element. For the pivot element, we first take a look in the row which relates to the objective function. In particular, we take a look at the two values, the -28 and the -42. And we select a negative entry, and in particular, we select the absolutely largest negative value, meaning they are both negative. So then we take a look, if we were to skip the minus sign, which one would be the largest one? That would be the 42. So we could also call this select the one which is negative and farthest away from 0. So here we will get the 42. So x2, or the column related to x2, that's our pivot column. Then next we need a so-called pivot row. For the pivot row, we need to calculate some things. So we work our way through the pivot column, and in particular through x3, x4, and x5 rows. And in each instance, we divide the right-hand side value by the value in the pivot column. Okay, this sounds a bit complex. I will show you here. So for the first instance, we have 1200 and we have 2 as an element. So we divide the 1200 by the 2. We get 600. Then we do the same thing for the next row. There we have 501. So we divide 500 by 1. We get 500. Finally, we have 1704. So we divide 1700 by 4. And we get 425. Then we compare all these results. And we select the row where the element is positive, strictly positive, so it cannot be 0. So where the element is strictly positive, and the calculations we did on the right side, so the right side divided by the element, is the smallest. So here we have the advantage, all three elements are positive, so we could work with all three of them. Then we take a look. The first one would result in 600, the second in 500, the third in 425. So the third one leads to the smallest result. So we select the X5 row as Pivo row. Then we have a Pivo column and a Pivo row, giving us with the 4 or thought for Pivo element. So the 4 which is at the cross of X2 and X5 is our Pivo element. And this element we need to calculate the next step. Before we do this, what is actually happening here mathematically? By selecting the Pivo column, we decide on which direction to take. If we were to do this graphically, we would decide on which edge to move along. Which edge will lead to the highest increase in profits. Then we decide how far we can move along this edge so that we still stay within our feasible area. If we were to take the first or second row and not the third one, so we would take one of the rows which has a larger result, we would leave our feasible area. So we always take the one which is the most restrictive. That's how we get our Pivo row. Pivo column, therefore, where to go so that we can get to our solution as fast as possible. Pivo row, decide on how far to move without leaving our feasible area. Well, and then at the next step, we're basically at the next intersection in our, graph. We switch from one area, so from one line, from one edge, which we move along, to another edge. This is done via the Simplex algorithm or the recalculation. So what we're going to do here, we copy our table, more or less copy this. So first off, we just copy all the entries which are not impacted by the Pivo element. So the X1 stays the same, the X3 and the X4 stays the same, and the Z as well. The X2 and the X5, because that's the two which are in Pivo column and Pivo row, they switch places. So we have down here the X2 and up here the X5. Then the real recalculation starts. There we have 4 different steps. In the first step, we consider the situation or the position where the Pivo element was. And there we enter 1 divided by the Pivo element. So here we have 1 divided by 4 is entered down here. That's a place where before the Pivo element was. Then, in the next step, we work our way through the Pivo row. In the Pivo row, as we can see here, we just divide each element by the Pivo element. So we have 3 divided by 4, giving us the 0.75. And for the value to the right, we get 1,700 divided by 4, so giving us 425. That's the Pivo row. Then we can also easily get the Pivo column. In the Pivo column, we also divide by 4, but not alone by 4, we also divide by -1. So on the part above the Pivo element, we have 1 divided by -4, so we get -1/4. Above this, we have 2 divided by -4, so we get -1/2. And in the top part, we have -42 divided by -4, so this gets positive. Then we have plus 10.5. That's the easy part. However, that's already the first 3 steps of only 4. And the last part, we take each of the old values, and from these values we take the corresponding, or we subtract the corresponding value from the pivot row, multiplied with the corresponding element from the pivot column. All of this divided by the pivot element. Okay, sounds really confusing. So let's take a look how this looks in a practical fashion. Let's start with the upper left one, so the entry in the objective function. Here we had minus 28. Then we go minus, so 28 minus the value in the pivot column, that's a minus 42, times the corresponding value in the pivot row, that's a 3, and this then divided by the pivot element, divided by 4. Then we can just enter this into our calculator, and we would get a new value of 3.5. The same fashion we can follow for all the other entries. So for the entry in the x, or the entry with x1, x3, before we had 1, then we go 1 minus the corresponding element in the pivot column is the 2. The corresponding element in the pivot row is 3. So we go 1 minus 2 times 3 divided by 4, because 4 is the pivot element. Again, if we introduce this in our calculators, we get as a result minus 1/2. The next one, that's the element below this, is 1 minus 1, because 1 stands in the pivot column, times 3, because 3 is in the corresponding pivot row, divided by 4, the pivot element. So if we do this here, similar as before, we get 0.25. Then we can do the same thing on the right hand side. Here we start with the one in the objective function row again. Here we had minus 2000 minus 42, because this is pivot column, times 1700, because this is the one in the corresponding pivot row, divided by 4, the pivot element. And here we get as a result 15,850. Now you could just learn this formula to go about and calculate the other 2 entries. In some cases, however, it makes sense to imagine the pivot element being one corner of a rectangle, and the value which you want to calculate, that's the other corner, or the opposing corner from the rectangle. Then you have 2 corners of the rectangle, and the values which you still need are the 2 remaining corners of the rectangle. I didn't draw this here because in some cases would be way too much to actually see this here. So this, however, would be one way to think about. Always try to think that there is a rectangle spanning from the pivot element to the element you want to change. And you consider all 4 corners of your rectangle in calculating the new value. Well, you can think about how this would look like for the value where before you had x3. Here it's 1200 minus, then we have 2 and 1700. So 1200 minus 2 times 1700, and again divided by 4, giving us 350. And finally, for the last value, we do 500 minus 1 times 1700 by 4. This will result then in 75. And here you might already get an idea why when we decided on the Pivo row, this was so important that we selected the row which led to the smallest result. Because if we would have selected one of the larger ones, we would have gotten negative values on the right hand side. This would be bad because this would mean we would leave our feasible area. Because the feasible area only consists, in our example, or in the fashion we work with this, with positive values for x1, x2, and for all the additional variables we added for our constraints. Okay, so far so good. This was the whole step of the Simplex algorithm. And now we could just continue doing the same step all over again. So here we would take a look at the elements in our objective function row. So here 3.5 and 10.5. And we would select the negative one, which is the furthest away from 0. We take a critical look here, however, we see there is no negative entry. And as soon as you achieve this, as soon as you achieve that all objective function values, coefficients, have become positive, this means we actually reached our optimal solution. So, meaning here the algorithm stops, we reached our optimal solution. We are at our optimum. Okay, what is the optimum? The optimum can be described that all the values, the variables, which are in the upper part, so the x1 and the x5, have a value of 0, and all the values in the lower part have the value corresponding to the values on the right hand side. So the x3 is 350, the x4 is 75, and the x2 is 425. Okay, we're not so much interested in x3, 4, and 5. We're more interested in x1, x2. So we see here x1 is 0 and x2 is 425. So this would mean do not produce any basic versions, only produce premium versions. And in particular, produce 425 premium versions. So far for the first question, we've been asked which combination to produce. However, we were also asked about what will be our overall profits. And that's where the right-hand side value of the objective function comes into play. Here the 15,850. Because this is actually our objective function value if this solution is realized. So if we only go for producing premium versions, and we produce 425 premium versions, we would get our result, our profit, as 15,850 euros. So that's the maximum we can achieve, the maximum profits which are possible. This then also already answers the second part of our exercise, of our task. So we found the optimal solution, and we directly found as well the profits related to this optimal solution. So we do not only know what we need to do, but we also know how well this will turn out in the end if we follow this strategy. And well, this then concludes this short session on the Simplex algorithm. Of course, practical problems usually are way larger, and even in some calculation examples, you might have to do more than just one step as we've done here. But I think already just talking our way from text to mathematical model, from mathematical model to working tableau, and then working through one step of the Simplex algorithm already gave us a good idea how the procedure actually works. In this context, I hope you enjoyed listening to this session. you learned something from this. And if you want to see more of this type of videos, feel free to visit the other parts of this general playlist. I say goodbye and until next time.